In this video, we're going to talk about three special bases: the binary, the octal, and the hexadecimal. Binary is base 2, octal is base 8, and hexadecimal is base 16. These three bases play important roles in computer programming and computer science, and they're easy to convert between because they are all powers of 2. We're going to start talking first about the binary system. So the binary system, as I said, is a base 2 system, and so therefore it has only 2 digits, 0 and 1. Now, just like any other base, if we have a base 2 system, remember that all of the digits in our number are going to be powers of 2. So we're going to have the 2 to the 0th power, which is 1, the 2 to the 1st power, which is 2, the 2 to the 2nd power, which is 4, 2 to the 3rd power, which is 8, 2 to the 4th, which is 16, 2 to the 5th, which is 32, and so on. So notice all of our digits, again, are just powers of 2. So we're just going to multiply by 2 to get the next digit. So we have the 2, the 4, the 8, the 16, the 32. So this one would be the 64, and the 128s, and so on. Now, every digit has to either be a 0 or a 1, which makes it real easy to convert a base 2 number into a base 10 number. Because if there's a 1, we add the place value, and if there's a 0, we ignore the place value. So for example, if I have the number 110101, okay, then I know that I have the first digit is the 1s, the 2s, the 4s, the 8s, the 16s, and the 32s. So I have a 1, I don't have any 2s, I have a 4, I don't have any 8s, I have a 16, and I have a 32. So I simply write the place values of the numbers where there's a 1, and I ignore the ones that have a 0 in. Now if I were to add all these up, 32 plus 16 is 48, plus 4 is 52, 53. So this number would actually just be 53 in base 10. So again, we simply find the place values and add those up. So let's do one more example. If I have 1110010, okay, I have no 1s, but I have a 2. I have no 4s, no 8s, but I have a 16, and I have a 32, and I have a 64. So now I would just add these. So 64 and 32 is 96, 112, and 2 more is 114. So this number is 114. If I want to convert from base 10 to base 2, it's just as simple. I just find which place values add up to the number I want to convert. So for example, if I have 71 and I want to find what that is in base 2, well, I know that I'm going to need a 64, so I'm going to have a 1 there. Okay, and then what's left? If I take 71 and I subtract 64, that leaves me 7. And to get 7, I need a 1 here, a 1 here, and a 1 here. So all the rest of these digits should be zeros. And let's check our work and make sure we did it right. So we have a 64 plus a 4 plus a 2 plus a 1. So that's going to be 68, 69, 70, 71. And we got it. So that means that 71 can be written as 1000111 in base 2. All right, now we're going to talk about base 8 or octal. Now in base 8, remember that we need 8 digits, so we will use 0, 1, 2, 3, 4, 5, 6, and 7. So these 8 digits are the digits that we use to form base 8 or octal numbers. Now the nice thing about 8 being a power of 2 is that if I look at any 3-digit base 2 number, Remember that the place values are powers of 2, so we have the 1s, the 2s, and the 4s. The biggest number that I can form in base 2 using 3 digits is a 7, 4 plus 2 plus 1. And that's the biggest number that I have in my octal system. And of course, the smallest number is 0. So I can form every number from 0 to 7 using 3-digit base 2 numbers. So that means that if I want to take, for example, a base 8 number like 725, and I want to convert this to base 2 or binary, I can simply write each digit as a 3-digit binary number. So for example, 7 can be written as 111 because we would need a 1 in this position, a 1 in this position, and a 1 in this position for those to add up to 7. And then for the number 2, we would have a 0 in the 4's position, a 1 here in the 2's position, and a 0 in the 1's position. So we could write that as 0, 1, 0. And then finally for the 5s, we would need a 1 in the 4's position, in the 1's position, and a 0 here. So this would be 1, 0, 1. And now I've actually just converted this 725 base 8 into this binary number. All right, so let's look at another example just to make sure we got it. So we're just going to take each digit and convert it to a 3-digit binary number. So suppose I have 7643 in base 8. All right, so for 7, remember I need a 1, and a 1 because I have to add all of these digits to get 7, right? For 6, I need a 1 in the 4's position and a 1 in the 2's position and a 0 in the 1's position. To get the number 4, I need a 1 in the 4's position and 0 in these two positions. So 1, 0, 0. And then finally, to get the number 3, I need a 0 in the 4's position and a 1 in the 2's and the 1's. So we have a 0, 1, 1. And we now have a base 2 number. So that's how we can easily convert from base 8 to base 2, is just convert each digit to a 3-digit binary number. Now similarly, if we wanted to go from base 2 to base 8, so suppose I have this base 2 number, then I can just group this into groups of 3 digits and then convert each group of 3 to a base 8 number. So I have these 3 digits, these 3 digits, these 3 digits. And then I can think of this, since there's not 3, I'll just put 2 zeros in front. So now I'm just going to convert each group of digits. So if I have 0, 0, 1 in base 2, remember that that's 0 4s, 0 2s, and 1 1. So this is just a 1. If I have 1 1 1 in base 2, that means all of these digits are 1s, and therefore I add all their place values. So 4 plus 2 plus 1 is 7. And then 0 0 1 is 1 again. And then 1 0 1 is 4 plus 1, or 5. So this number is equal to 1715 in base 8. All right, one more example of that, and then we'll move on to hexadecimal. So let's suppose I have 10 11 00 1 0 1, and this is a base 2 number, and again I want to convert it to base 8. So again, I'm going to just start grouping my digits in 3s. This group of 3, this group of 3, and this group of 3. And then I'm going to convert each group. So this is a 4 and a 1. so this is 5. I have a 4, no 2's and no 1's, so this is 4. And then here I have a 4, no 2's and a 1, so 4 and 1 is 5. So this number is 545 in base 8. Now in base 16, or the hexadecimal, we have to have 16 digits. And of course we know that in our system we only have 10. So if I write them down here, since we have a base 16 system, we need to have 16 digits. So there's only 10 here. So what we do to represent the other digits is we just start using capital letters. So A represents the value 10. B represents the value 11. C represents the value 12. D represents the value 13. E represents the value 14. And then finally F represents the value 15. And now we have 16 digits or numerals, so to speak. Okay? So a number in base 16, of course, remember each digit is a power of 16. And so, for example, if I have A37 in base 16, or in hexadecimal, that means I have a value of 10 in this digit, a value of 3 in this digit, and a value of 7 in this digit. And all of my digits are powers of 16. So I have the 16 to the 0, or the 1's. I have the 16 to the 1, or 16. And then I have the 16 squareds here, which is the 256's. So that means that this number, A37 in base 16, means I have 10 256's. Then I have 3 16's, and then I have 7 1's. So I have 2560 plus 48 plus 7, or 2615. All right, so, but what about converting between base 2, binary, and base 16, which is done in computers a lot? Well, similar to what we did up here with base 8, if we look at a 4-digit binary number, remember in binary we have the 1's digit, the 2's digit, the 4's digit, and then we'll have the 8's digit if we have a 4-digit number. So if we add 8 plus 4 plus 2 plus 1, we get 15, and notice that 15 is the biggest value that we can have in single digits in our hexadecimal system. So what we can do is we can write each of these as a 4-digit number to convert this from base 16 to base 2. So if I want to write each of these as a 4-digit number, to write A, which represents 10, as a 4-digit number, I would need a 1, then a 0, and then a 1, and then a 0, because I would add the 8 and the 2 to get the 10. So this would be my A. And then to get the number 3, I'm going to have a 0, a 0, a 1, and a 1, because 2 plus 1 is 3. So 0, 0, 1, 1, and that gets me the 3. And then to get the 7, I don't have any 8's, so that's a 0, but I need 4 plus 2 plus 1, so I need a 1, 1, 1, and that gets me the 7. And that means that the number A37 in base 16 is equal to 1010 0011 0, 1, 1, 1 in base 2. So just like we did when we went from base 8 to base 2, where we took each digit in the base 8 number and made it a 3-digit binary number, in base 16 we take each digit and make it a 4-digit binary number. And then of course, to go the opposite direction, to go from base 2 to base 16, instead of grouping in 3s, we'll group in 4s. So for example, if I have a number like this in base 2, and I want to convert it to hexadecimal or base 16, I'm going to start grouping in 4s. So I'm going to put these 4 digits, then I'm going to put these 4 digits, then these 4, and then of course I can put 2 zeros in front here to make that a 4-digit number. And now I start converting, remembering the place values are going to be 1, 2, 4, and 8 in binary. So if I have a 0, a 0, a 1, and a 1, this is going to be 3. And then the next one I have a 1 here, a 1 here, and then these two are zeros, so 8 and 4 is 12. Remember, in base 16, 12 is represented not with the symbols that we typically use, but with this symbol C, right? So since this value is 12, we'll use the symbol C to represent it. All right, then we have a 1, 0, 0, 1. So a 1 here and a 1 here is a 9. And then finally we have a 1, 1, 0, 0 again. So 8 and 4 is 12, and 12 we use the symbol C. So that means that this number in base 2 is equal to 3C, 9C in base 16.